Welcome to another deep dive. Today we're taking a plunge into one of the most talked about concepts swirling around large language models, LLM, this whole idea of emergence. So you've heard the buzz, right? These claims that AI systems suddenly gain incredible, almost magical capabilities as they scale up.
Absolutely. And what's truly fascinating, I think, is that emergence isn't just some trendy tech word. It actually has a very specific, quite rigorous meaning in complexity science. So our mission today is really to dig into a stack of fresh sources, including a brand new paper published just yesterday, June 16th, 2025. It's by Krakauer, and Mitchell from Santa Fe Institute and Johns Hopkins. We'll unpack what emergence really means, scientifically, and then look at whether LLMs truly exhibit it and what that tells us about their journey, and just maybe their path towards something like intelligence.
All right, let's dive deeper into this then. We'll explore the claims, nail down those scientific definitions, and ultimately help you decide if we're witnessing, true emergent intelligence or something else entirely. Okay, so before we get specifically into the LLMs, let's set the stage a bit. When scientists talk about emergence, what exactly are they referring to? Because it sounds like it's a bit more profound than just, something unexpected happened.
Oh, it absolutely is, yeah. In complexity science, emergence describes how complex new behaviors or properties can arise from relatively simple interactions of many parts. The whole is truly more than the sum, as they say. Think of it like this. A single brick isn't a house, right?
Right.
But millions of them, interacting in specific ways, following certain rules, they emerge into a house. Or think about individual water molecules. They don't have wetness on their own, but a vast collection of them does. The key insight, really, is that we can then describe these complex patterns with surprisingly simple, higher-level theories. It's like zooming out. For instance, to build a bridge, we don't need to understand the quantum mechanics of every single atom in the steel.
Definitely not.
Classical physics, which itself emerges from quantum mechanics at a larger scale, is perfectly sufficient. Or think about fluid dynamics, instead of tracking every single molecule, which would be impossible.
Yeah, computationally insane.
Exactly. We use simpler macroscopic variables, things like total mass or pressure, to predict and describe how the fluid behaves. This coarse-graining, basically simplifying by focusing on the big picture, it leads to enormous efficiency. Huge savings in how we describe and control these systems.
That idea of simplifying complex systems down to more manageable descriptions, that feels really powerful. And the paper we're looking at argues that, at a minimum, true emergence requires the system to internally reorganize itself.
Right. Yes, precisely. It needs to allow for a new, often simpler description that kind of screens off or lets you ignore the messy microscopic details.
Okay, screens off the details.
But crucially, this new, simpler description still needs to be predictive. It has to help us understand these complex systems. So if that's the scientific gold standard, how does this popular idea of emergence in LLMs actually stack up? Because, from the outside, those jumps in performance, they look pretty remarkable, don't they? They really do.
Okay, so with that scientific definition hopefully a bit clearer, let's turn to the large language models. We know these are deep neural networks. They're trained on absolutely vast amounts of text, and fundamentally their main job is just predicting the next word in a sequence.
Seems simple enough on the surface. Right, but it's what they manage to do beyond that simple task that has everyone talking. You get these impressive abilities like learning syntax, generating computer code, writing in basically any style you ask for, recalling factual information. And it's these surprising abilities that really sparked those claims of emergence within the LLM community. For instance, there was a pretty seminal paper back in 2022 by Wei and colleagues, Emergent Abilities of Large Language Models. They define these abilities as ones that are, quote, not present in smaller scale models, but are present in large scale models, and crucially also cannot be predicted by simply extrapolating performance.
Okay, so not present in smaller models and these sudden jumps. Can you give us a concrete example? What's a classic case that really illustrates this kind of behavior in LLMs?
Sure. A classic one that's often cited is three-digit addition. Seems simple for us, but for an LLM. So a model with maybe 6 billion parameters might achieve only, say, 1% accuracy. Really poor.
Wow, okay. Basically guessing.
Pretty much. Scale it up to 13 billion parameters. It's still only around 8%. But then seemingly out of nowhere, you train a model with 175 billion parameters, and suddenly it hits 80% accuracy on three-digit addition. That looks like a sharp, almost discontinuous leap, a real qualitative shift.
That certainly sounds like a textbook case of a sudden leap. Very dramatic. But, in science, there's always scrutiny. Is there a counterargument? Do these jumps hold up?
That's a great question. And yes, there are counterarguments. Some follow-up studies, like one by Schaefer and colleagues, argue that if you use different, maybe more continuous metrics for success,
Different ways of measuring.
exactly, then these improvements can appear more gradual, less abrupt. It might depend heavily on how you measure success and the specific task you're looking at. That said, the debate isn't settled. Others still question whether all improvements are truly continuous across all tasks. It's an active area of research. And beyond just these sharp performance jumps, other claims of emergence involve abilities the LLMs weren't explicitly trained for at all. Things like numerical understanding beyond simple arithmetic or analogical reasoning, legal reasoning. Some even claim they form internal world models.
Okay, this brings us to a really crucial point the paper makes. It suggests LLMs are a unique case when we discuss emergence. They introduce this distinction, knowledge out versus knowledge in emergence. Can you break that down? It sounds like it really reframes how we should be thinking about these models.
It really does. It's a key distinction. So knowledge out, or KO emergence, that's what you typically see in physical or chemical systems. Think simple interactions among simple components giving rise to complex structures, sort of, spontaneously, like a quartz crystal forming its structure or its piezoelectric properties. Those emerge from simple atomic bonding. Nobody designed it with that property in mind at the atomic level. The complexity comes for free, you could say, through self-organization. It's intrinsic.
Okay, so arising from the system itself, what's knowledge in then?
Knowledge in, or KI emergence, is different. It's more characteristic of complex adaptive systems. Things like biological organisms, brains, maybe even economies. Here, complex behaviors or structures arise because the system has mechanisms to actively extract and internalize vast amounts of knowledge, meaning structured information, from complex environments that already exist. It's about learning from the world.
Right, absorbing information from outside. So what does this fundamental difference mean for how we categorize LLMs? Where do they fit?
LLMs are definitively knowledge-in systems, no question. They are trained with massive amounts of pre-existing text data, the knowledge of the internet, essentially using very sophisticated machine learning algorithms. They are literally designed to absorb and compress this external knowledge. And because of this KI nature, just observing impressive external behavior isn't enough to claim true emergence in that strict scientific sense we discussed.
So just because it can write a poem doesn't mean it's truly emergent.
Not necessarily in the scientific sense, no. We need to see evidence of a genuine, coarse-grained internal reorganization within the network itself. A reorganization that screens off those microscopic details, remember. If the behavior is merely a result of extremely complex programming via the training data, no matter how impressive it looks, it's not truly emergent according to that rigorous definition. It's learned capability, not necessarily emergent structure.
This paper, the new one, offers a framework, right? 5 key principles to analyze emergence more rigorously: scaling, criticality, compression, novel bases, and generalization. How do the LLM claims hold up against these criteria?
Good question. Let's take scaling and criticality first. We mentioned those sharp accuracy jumps in LLMs. They look a bit like phase transitions in physics, like water suddenly freezing into ice at a critical temperature.
Right, that sudden shift.
But the control variable in LLMs isn't simple like temperature. It's this complex mix of model size, dataset size, architecture details, training time. It's highly multidimensional, not a single knob you turn. And crucially, for true emergence related to criticality, we'd want to see evidence of a global reorganization of the internal structure of the model, not just a change in its external performance metrics.
Are we seeing any hints of that internal change?
There's some promising, though still early, work. A recent study in preparation by Guth and Menard suggests there might be qualitative changes in how the neural networks encode information, changes that happen alongside these performance jumps. And another study by Chen and colleagues showed nonlinear reductions in the model's error rate that seemed correlated with the emergence of new internal structures related to syntax. So this is getting closer. It's starting to probe the inside and linking it to capability.
Okay, what about compression? You mentioned simplifying descriptions earlier. Does that play a role here?
Compression is absolutely crucial, yeah. Emergence often involves the system discovering and exploiting lower dimensional, more compressed, coarse-grained ways to represent information internally. It's about finding the underlying patterns, the simpler rules. There was that interesting example of Othello GPT, a transformer trained to play the game Othello. It appeared to develop an internal compressed world model, like an internal representation of the game board state.
That sounds pretty emergent.
It does, on the surface. However, a necessary caveat here is that later studies question how truly parsimonious, how elegantly simple and efficient these internal models actually were. Some suggested it might have been more like a complex bag of heuristics, a collection of learned tricks, rather than a genuinely compressed fundamental representation of the game.
Ah, okay. So maybe not as clean as it first looked.
Potentially. And critically, the causal link wasn't definitively proven. Did that internal model cause the better predictions in a newly emergent way, or was it just correlated with good performance learned through massive training? That link is key and often hard to establish.
Got it. And the last two principles, novel bases and generalization. Do LLMs discover genuinely new ways to represent information, and can they generalize that knowledge effectively?
On novel bases, meaning, does the LLM discover fundamentally new internal alphabets or core principles for encoding regularities in the data? Honestly, very little is definitively known yet. It's hard to peek inside and understand the language the model is using internally. As for generalization, which is a hallmark of intelligence, the ability to succeed in qualitatively new situations, not just variations of training data. LLMs show some ability here. For instance, some can extrapolate the behavior of dynamical systems, but often these emergent abilities that look like generalization have lacked true robustness. They sometimes fail unexpectedly or seem to rely on memorizing patterns or shortcuts present in the vast training data, rather than deriving general principles they can apply broadly.
Okay, so it seems the picture for even just immersion capabilities in LLMs is, well, complex. It requires much more digging into their internal workings, not just being impressed by the output. But the paper takes this even further, making this really critical distinction between emerging capability and emergent intelligence. This feels like the heart of the matter, doesn't it?
I think it really is. It forces us to ask a fundamental question. What do we actually mean by intelligence? For humans, we generally think of intelligence as this general capacity for learning, for solving problems efficiently, quickly, and crucially parsimoniously, using minimal energy and resources.
Doing more with less.
Exactly. It's about doing more with less. Using analogy, for instance, to transfer concepts and adapt them from one domain to a completely different one. Think of a brilliant mathematician or physicist. They strive to explain an ever-increasing range of phenomena with a surprisingly modest set of fundamental ideas or equations. They don't need a brand new complex theory for every single observation.
Right. Elegance and simplicity are valued.
Precisely. Now contrast that with, say, a calculator. Calculators are incredibly capable. They blow humans away at arithmetic. But we don't usually call them intelligent, do we?
No, definitely not.
Because they can't form analogies, they can't easily modify their rules to tackle entirely new kinds of problems without someone explicitly reprogramming them. They have capability, but not that flexible, adaptive understanding.
So it's not just about performance. It's about the nature of that performance, how you get there. Is it deep understanding or just incredibly powerful computation? That makes LLMs seem potentially more like support calculators, astonishingly capable, yes, but maybe not intelligent in that human sense.
That's exactly the argument the paper makes. It suggests LLMs are, at best, demonstrating emergent capability. And often, it's what they term hugely over-parameterized capability. They sometimes exhibit a kind of Rube Goldberg logic, those incredibly complex, convoluted machines built to perform a very simple task.
Yeah, no.
It's like that sometimes. Massive complexity, huge computational cost, incredibly inefficient energy use, all to achieve a capability. Human intelligence, by contrast, is often described as a low-bandwidth phenomenon. We transmit incredibly complex ideas, scientific theories, emotional nuances, jokes with just a few words, maybe a simple diagram. We don't need to share gigabytes of synaptic weights the way you'd copy an AI model.
That's a powerful contrast, the efficiency of human communication and learning.
And human understanding has causal power, as the paper puts it. Think about teaching someone a complex concept verbally. If they get it, sometimes in just minutes, their brain, their neural network, has rapidly reconfigured itself based on that high-level instruction, allowing them to solve new problems. This instruction-mediated emergence, this ability to rapidly acquire new generalizable capabilities through understanding high-level concepts, that's a hallmark of human intelligence, and something we haven't really seen convincingly demonstrated in LLMs yet.
Wow. So the paper leaves us with this really profound thought. Intelligence is a property of understanding and only incidentally a matter of capability.
Exactly. Capability is necessary, perhaps, but not sufficient. Understanding is the key differentiator.
Well, that was a truly illuminating deep dive. Really fascinating.
Yeah.
From today's discussion, it's become much clearer that while large language models definitely demonstrate astonishing, often surprising capabilities, the scientific definition of emergence in this context is, well, it's much more nuanced than how the term often gets thrown around.
Absolutely. We've seen that true emergence, scientifically speaking, demands more than just impressive output. It requires evidence of new, compressed internal descriptions, new ways the system organizes itself internally that genuinely screen off those microscopic details. And that leap from emergent capability, even if proven, to emergent intelligence is a really significant one. It seems intelligence, at least as we understand it in humans, is characterized by things like parsimony, analogy making, and this incredible ability to learn and adapt using a less is more approach.
So what does this all mean for you, the listener, as you navigate this incredibly fast-moving world of AI? Maybe the next time you interact with an LLM and you're impressed by what it can do, and it is often impressive, take a moment. Consider not just the capability, but also ponder this. Are you witnessing the first glimmers of true understanding emerging? Or are you seeing the extraordinary power of a system that excels at doing more with more, a master of capability without necessarily grasping the underlying why? It's a fascinating question, isn't it? And one worth continually exploring as these systems keep evolving.